Ok, bonjour. Merci d'être venu. Welcome. Thank you for coming. So, last time, it's Pierre-Antoine. Salut Pierre-Antoine.
Hello.
So, last time we discussed the general principles of broken symmetry. Huh? We said that sometimes the interactions are such that the preferred state in the presence of an infinite system will have a symmetry that is not the symmetry of the Hamiltonian. And we saw how to treat this problem in simple way. We guessed that there would be a lambda functional f of some order parameter m that would be equal would be a power series in m 4, and that the most probable state is the one where the derivative is 0. And that was minimizes the free energy. And here, what we are treating is an example of what we call the second order transition. So this is am plus b m cube equals 0, and that's m times a plus b m squared equals 0. So that if a is negative, there's a solution. And we also said that in general, for a continuous symmetry that is broken, that would be Goldstone modes. In other words, modes that restore the symmetry, or in other words, if the frequency goes to 0 at the wave vector of the broken symmetry state. So, and then we said, okay, let's try the ferromagnet. So what we did for the ferromagnet is to guess that there's a solution where n up minus n down is not equal to 0, so it's equal to some magnetization m. And then just by writing we did Hartree-Fock, and then just by writing the expression for n up and down in terms of the Fermi function, for example, the Fermi function for the up electron would be epsilon k plus u and down minus mu for the up electron. So if we write the equation for this n up minus n down, then that becomes a nonlinear expression, right? So we expanded to linear order in this, and we found that if this is less than 0, then indeed there's a solution. A would be 0. So that's and that's the density of states at the Fermi energy. So we have to guess that there would be an epsilon tilde k that this depends on the spin, and we actually I said we did Hartree-Fock, but the way we really did it is just by substituting in this variational principle a trial Hamiltonian 0 here, h0 tilde. That would be sum over k of zeta k sigma. I mean, this is h0 minus mu n, zeta tilde k, k sigma, k sigma. So by minimizing this, we got basically the equivalent of this expression. I didn't derive this, but we could. I mean, if we just expanded this right-hand side with this ansatz and expanded the right-hand side. But we get directly to this equation using this variational principle. So that's basically what we discussed last time. Is this okay? Do you have some questions? Okay. So today I will derive this variational principle because I told you that I asked you to accept it without proving it. So I will prove this. And then we will look at this problem from the Green's function point of view. Okay. And I will argue that there's a mean field, which is this mean field is this difference here between the M, but there are still interactions in the system. So sorry, I mean, as you see, this is not the order of the notes. So I will need to rewrite the notes. I think it's better to present it this way. Then I will show you that we can, in the normal state, we can see that the normal state is unstable. We can see that in the normal state, at some point, something happens. I mean, we get a susceptibility, a spin susceptibility that's negative, which we should not be. And the criterion for the instability is precisely the same as the one we have here. Then I will show you that there are collective modes in the system that are called paramagnons, whose frequency goes to 0 as we get closer and closer to the phase transition. So that's called critical slowing down. So in other words, in this case, for a second order transition, we can see it coming from the normal state. That's what I will describe here. And then I need to show you these Goldstone modes, and that will come from computing the transverse susceptibility. So in the ordered state, if we choose to break the symmetry between n up minus n down, we have a magnetization this way. And if I try to excite the particles, there's a gap, okay? That's related to this difference. But now if I look at the transverse susceptibility, if I turn things around, then you see that at 0 wave vector, so at q equals 0, there would be a 0 frequency mode. So that's the Goldstone mode. And then this will get right back to the Mermet-Wagner theorem and the Kanamori-Bruckner screening that I explained to you earlier with the TPSC. So in other words, we are using the simple example of the ferromagnet to show mathematically all these concepts we discussed with the hands. Okay? Is that okay? Do you have some questions? I hope to finish this today. If not, I will need a little bit of time Friday, and then we will go to BCS. But I hope we will finish early next week. Okay, so let's prove this quickly. This is based on the following inequality. So minus trace rho is a density matrix. Log rho is less than or equal to minus trace rho log rho prime. So rho is a density matrix and rho prime also, but it's not the same density matrix as here. And this you will see, if you don't remember, this is the entropy. So you will see this later if you don't remember. So to show this, let's proceed like this. I can write minus sum over m. M is the eigenbasis for rho. Okay, So then rho in this basis, that's the eigenbasis, is just a probability of being in state M, and it's a diagonal. So the log of rho in a diagonal basis is log of Pm. Now I put this on the left, so that's a plus sum over M and M prime of M rho M prime log rho prime of with M. Okay, so I just put a complete set of states here, and I wrote the trace explicitly. So this piece here is just plus sum over M prime. M is the eigenbasis for rho is here. So that's Pm M prime. N and M prime are not necessarily orthogonal, they're just different bases because rho prime is anything. Now, if M prime is an eigenbasis for rho prime, this means that this is just log of P prime of M prime, and I still have M prime M, okay? Now, this piece I can write as minus sum over M prime M sum over M prime of Pm log of Pm. Okay, I have done nothing here because M prime is just a complete set of states, and M was the eigenbasis for Pm. But you see now I can combine these two terms. That's the idea. So this is equal to sum over M prime of M prime M minus Pm log of Pm plus Pm log of P prime M prime. Okay, and this was on the left-hand side, so that's less than or equal to 0. Now to prove this, I will use a simple inequality. A convexity inequality, which is just that the log of y minus y is less than or equal to minus 1. Okay, so to prove this, I show that let's set the first derivative of the left-hand side equal to 0. So that's 1 over y minus 1 equal to 0. Okay, so the solution is that y equals 1. Okay, and at y equals 1, I get minus 1, right? Because log of 1 is 0, so I get minus 1, so it's minus 1. So I get the equality at this point. Now, if I look at the second derivative of this, then the second derivative is minus 1 over y squared, which is always less than 0, which means that the curve is like this. Okay, and it has a maximum at minus 1. So if I use this here, I can replace the log of P prime M. So this is less or equal to 1 minus 1 plus y. So I will use this here. So this is less, so this thing here, and it has a plus sign, is less than or equal to let me come back, let me do something first. Okay, I combine these two things. So, so that's equal to sum over m prime, m prime, m prime, m times p m log of p prime m prime divided by pm. Okay, the minus sign here means that I can put log of p to the minus 1, and the log of the product is log of a sum of a log is the log of a product. Okay, now I can use this inequality. So this is less or equal sorry, I have no room anymore. Well, okay, I will erase this. You need to remember it. We will see it in a moment. So that's less than or equal to all these sum m prime modulus square m prime, and here I have pm, and I have y minus 1. So that's p prime of m prime over pm minus 1. So that's, see, this whole thing is just p prime m prime minus pm. But both of these are normalized. You know, if I sum over, in the case of m prime, I can do the sum over m, and using the complete set of states, then I just have the sum over m prime of p prime of m, and that's equal to 1, and this is equal to 1 also. So that's less or equal to 0. Okay. So now let's go back to this and use it to prove this. So what I will do is I will do my trial Hamiltonian here, 0, 0, 0. And here I will put the real Hamiltonian, row of the Hamiltonian I want, okay? So then it means that I get minus a trace of rho 0 log rho 0 is less than or equal to minus trace of rho 0 log of exponential of minus beta h minus mu n divided by z. So that's easy. If I take the log of an exponential, it's just the argument. So the first term is just the minus, this disappears. So the first term is just beta times the expectation value of h minus mu n in the basis 0. Okay, in this, for this trace, I mean the trace over not the basis, but the row, the trial Hamiltonian rho 0. And then I have another term, which is, so the log of z, so minus log of z, so the minus disappears again. So I get a plus log of z. Okay, because again, the trace of rho 0 by itself, the z is the number, trace of rho 0 is 1. So, yeah. So this is divided by, temperature. And on the left-hand side, I will get the same thing, except that I will get H0 here, okay? So then here it is H0 minus mu n in the basis 0 divided by T plus log of Z0. So you recognize the entropy here, because why? Because you remember that the ground potential, which is minus T log Z, is equal to E minus mu n minus Ts. So it means that if I put this on the left-hand side, or if you want, I can do minus E plus mu n and then I can get rid of the minus sign. And I can divide by temperature. Okay, which is this. So that's true in any basis, in any ensemble, the grand canonical, microcanonical. This is the entropy is always this. But here we don't really care about the fact that the entropy. We just want to rewrite some we just want to find this inequality. But this is easy now, because we just put this on the left-hand side. So that's minus log z is less than or equal on the right-hand side. So that's minus log of z0. And here on the right, I have plus. Okay, the mu n disappears. I take the same value of n at both places. So I have h minus h0 computed in the 0 thing, divided by temperature. So I multiply by temperature. Okay. Fine. Okay. All of this to just to prove this little theorem. Sorry, it takes so much time. But you realize it's an important theorem, right? Anytime you want to find, if you have an idea for a broken symmetry and you want to show that this broken symmetry minimizes the, gets you closer to the real free energy, you just put your trial Hamiltonian or in this thing, and this is it. You're done. So this is what we have done with the ferromagnet. We assumed that these two things were different, that up and down were different, and we found a solution for this. Any questions? Okay. So now from from the point of view of Green's functions. So from the point of view of Green's functions, what we can do when I add h minus mu n, I called it k. So this is not really a very nice, let me, in the case of h0, let's call this epsilon. Then the Green's function for this guy, the Green's function g will be just 1 over ikm minus epsilon k tilde sigma. So that would be the Green's function for sigma plus mu. And we know that if we want the number of particles for this, the number of particles, for example, the up thing from this Green's function, we do the sum over Matsubara frequency. It gives a Fermi function. And then this will be just 1 over n sum over k of f of epsilon tilde k up minus mu. So now how do we find this epsilon k tilde? From the point of view of effective medium theory, what we want is that this epsilon k tilde gives a self-energy that is 0 at the Hartree-Fock level. Okay, so at the Hartree-Fock level, the self-energy sigma will be equal to, for a spin sigma, will be equal to u n minus sigma. It's this term that used to vanish for the Coulomb interaction in the Jellium model, but here we have a contribution. So u n minus sigma. But we have to remember now that the Hamiltonian H is H0 tilde plus interactions plus H minus H0 tilde. And this we treat now as a perturbation. H0 tilde is what we have, and this is perturbation. So it means here that what we are doing is we are adding sorry, here I have H0 minus H0 tilde. I put the interaction explicitly outside here. So that's plus epsilon k minus epsilon k tilde equals 0 sigma. That's independent of sigma. So that gives me the result I got last time. Epsilon t with the variational principle. Epsilon k tilde sigma is equal to epsilon k plus u n minus sigma.
Quick question. I think I missed why we need the self-energy to be 0.
This is what we don't need it. We don't need it. It's just a way to derive mean field theory. In other words, you take a H0 tilde that will be such that okay, this is what I'm left with. That will be left such that the self-energy at the Hartree-Fock level is 0.
Okay.
And then you see that it's equivalent to all this that we did. So this is like effective medium theory. Now, what I mean by residual interaction is precisely that we have something left here. Okay. So this is just the Hartree-Fock self-energy. but we still need, I mean, here we still have U. We still have U and up and down. So we will have the same diagrams as before. The only difference is that we never have self-energy insertions that are Hartree-Fock-like. Okay, so the corrections to the self-energy will involve U, but we never put Hartree-Fock term because they're always canceled by this counter term. Okay. Now, normal state instability. What do I mean by this? Well, let's go back to the normal state. So the Green's function is this. And now I compute the susceptibility. So the spin susceptibility of Q and omega is chi0 of Q omega divided by 1 minus U over 2 chi0 of Q and omega. So So now the way to find there's an instability or a phase transition in this, when it's a second order transition, is to look at zero frequency. So zero frequency is thermodynamics. And what we will find is that there's a wave vector Q such that this denominator becomes zero or negative at low enough temperature. So let's see what I mean. Low enough temperature or large enough interaction. Okay. So what is chi0 at zero frequency? So chi0 in general of Q and omega is equal to -2 sum over wave vectors. Okay, it's a product of Green's functions we saw here, and we do the sum over Matsubara frequencies, and we're left with f of zeta k, where zeta k is epsilon minus mu, minus f of zeta k plus q divided by omega plus I eta plus zeta k minus zeta k plus q. This is the Lindard function that we derived already. So at zero frequency, it is this. And in a ferromagnet, the instability is at Q equals 0, right? Because we put all the spins up everywhere. So if we take the limit Q goes to 0 of this, what do we get? So this is zero frequency now. This is equal to -2 sum over k of df of zeta k d zeta k. Okay, when Q goes to 0, this is just a derivative. And what is this? Well, at zero temperature, this is just a minus this is just a delta function of zeta k at the Fermi energy. So here I can do this. I can do -2 times the integral over energy of the density of states times df d epsilon, epsilon minus mu, and minus df d epsilon is we said at 0 temperature is a delta function. So that's the density of states at the Fermi energy. I wrote n of 0 last time, but because this is usually what we see, but it's just a question of definition. And there's a 2 here. So you see when I substitute here, I get 1 minus u times n0. So if u is large enough that this becomes negative, I have a susceptibility that's negative. And from the point of view of thermodynamics, that's an instability. So the condition that I had, that I had a solution for m is the same as the one I find from the normal state, for the normal state to be unstable. So when I was telling you that the perturbation theory cannot go, cannot cross a phase transition, it can see it coming, but it cannot go on the other side. This is what I mean. Okay, the perturbation theory has diverged here at the phase transition. So we break the symmetry, we go then on the other side, and we treat a state that is ferromagnetic. Okay. Now we can see it another way. We can see that there's at low frequency, if omega is small, there are collective modes whose frequency goes to 0. So let's put back omega here. And then here I have omega plus I eta plus this. And now this is a function of frequency. And one way to see spin fluctuation is to do neutron scattering. Okay. And neutron scattering, remember the beginning of the class, it measures the structure factors, S of Q and omega. So we are still in the normal state. And let me erase this. So the fluctuation dissipation theorem tells us that S of Q and omega is equal to 2 H bar equals 1 here. E1 minus E to the minus beta omega times chi double prime of Q and omega. So that's what the neutron scattering would measure. Now at 0 temperature, beta is infinite. So it means that we see a response only for positive frequency. Okay. Okay. So what would be the answer? The answer would be this. The answer would be that if I plot this S of Q and omega as a function of frequency, it will be something like this, with a peak here that is located at omega is about C to the minus 2 times VFQ. So as Q goes to 0, the frequency goes to 0. And even in the vicinity of Q equals 0, even if Q is not equal to 0, you see I have the correlation length to the power minus 2. Correlation length becomes large, so this becomes small. So I will have a soft mode. That's another thing that shows up in phase transition, soft modes. So this is called critical slowing down. since the correlation length is large, it takes a long time to flip the spins, and that's characterized by this. Okay, so that will be the result we will find. And so we will not worry about factors. So let me drop this factor of 2, and let me just write this chi double prime of Q and omega. To be proportional to chi double prime 0 over 1 minus u chi prime 0 square plus u times chi double prime over 2 square. Okay, the imaginary part of this, we already saw this structure with it was with the spectral weight, but if you compute the imaginary part, that's the way it comes out. So chi double prime is the imaginary part of 0 here, and chi prime is the real part of this quantity. So we need to just to look at chi double prime of 0. But what will happen with this is that as q goes to 0, this becomes c to the minus 2. This becomes the inverse correlation then, because if we expand this near the instability point, we will get a term that's of order q square, and a term that will be 0 at the phase transition. So this piece here will be c to the minus 2. And we just need to focus on this chi double prime of 0. So chi double prime is this. So I get minus, so that's plus pi times delta of omega plus zeta k minus zeta k plus q. Okay. Now, zeta k minus zeta k plus q is equal to, okay, k squared over 2m. So that's k squared over 2m also. There's a cross term k dot q over m. I will write this as minus v Fermi times q, because q will always be small. And then there's a term that's q squared over 2m. So q is small, so I will neglect this. And neglect this, and this is a dot product. So here I get omega minus VFQ cosine theta. And this I will expand as well. Okay, so I will write as df d zeta k times zeta k plus q minus zeta k, and there's a minus sign here. Okay, so I think so. Let's see. So that's a derivative, and I expand around what? I expand around zeta k. So I get zeta k plus q minus q. Equal to f of x minus f of x minus df dx times y. Okay, so that's what I. what I write here. So again, this is the same thing here. So this is VFQ cosine theta. So now I can do this. I can do this. I can divide by VFQ here. And that will divide by VFQ also. So I get rid of this. Okay, because I have delta of omega, the VFQ times all of this, and delta of A times X is equal to 1 over A times delta X. Okay, so that's what I did there. Now I can do the integral. Now I can change this into an integral. So I will have some integral of d cosine theta and an integral over energy times density of states again. Now the cosine, I can do the integral now over cosine theta, and that will give me VF omega over VFQ. So there's a bunch of constants I could compute that I did not compute, but okay, this is a constant times omega over VFQ. So when I substitute here, I have c to the minus 2 plus some constant times omega over VFQ square. Okay, there's something I don't understand now. And here I have omega over VFQ. So you see, this is why it goes to 0 here. There's an omega. That's okay because it's supposed to be odd, so it goes to 0 here. And then you need to find where is this this maximum. And so you need to differentiate this, and this is what you will find where the maximum is. Yeah, it's not so easy to see, but that's what happens in the end. Okay. Okay, now let's go to, I will stop here, but I want to start this calculation here of the transverse susceptibility in the ordered state, okay? So in the paramagnetic state, whether you're looking at the spin fluctuations like this, or longitudinal or transverse is the same thing. But in the ordered state, there would be a difference between longitudinal and transverse. Okay. If you look at the SZ, using the type of thing that I just showed here, you find that there's a gap, that you cannot excite, you cannot change M unless you pay this energy. But in the transverse direction, it will be different. There will be the ghost hormone. So how do we find this? Well, first, I need to discuss a little bit about spin. So spin in the second quantization is some spin at site I, for example. Well, or let's write this, spin at S of Q is equal to sum over K of C dagger K. Alpha is the spin index here, times the Pauli matrix, alpha beta, times the CK plus Q beta. So if you look at Q equals 0, and you look at the SZ, SZ for Q equals 0 is just sum over K of C dagger K up, CK up, minus C dagger K down, CK down. Huh? Because why? Because this sigma Z is equal to 1, 0, 0, minus 1. Now, what is Sx? What are Sx and Sy? So let me just talk about the Pauli matrices. Let's focus on the Pauli matrices. So I will, so Sx is 0, 1, 1, 0. I dropped the dH bar over 2 here everywhere, you understand. So Sx is this, and Sy I put Z on top, okay. Sx, Sy is equal to 0 minus I 0. So if I define Sx plus I Sy, it's equal to, let's see, I have only this that will survive. So it will be equal to 2 times 0, 1, 0, 0. And Sx minus I Sy is equal to 2 times 0, 0, 1, 0. So that's called S minus, and that is called S plus. So what we will compute is the susceptibility S plus, S minus. So, because if I look at S plus, S minus, plus S minus, S plus, the cross terms will disappear. These Sx, Sy don't commute, but they will drop out from this sum. This will be equal to, 2 Sx square plus Sy square, or in fact, there's a 2 here already, so it will be a 4. No. This will be this divided by 2. Okay, so we will stop here. Next time I will compute this susceptibility, okay, this chi plus minus and this chi minus plus. Because why? Because you see here, there's only one component, and this component here flips the spin. If I have a down spin, it goes to up. That's why it's called S plus. And S minus, if there's a down spin, it goes to plus. So for example, S plus at Q equals 0 will just be this. So that will give me diagrams that are like this. Let's say up, down. So I have S plus that flips down to up, and S minus that flips minus to up. So it will be the same diagrams, but now in the ordered state. Okay. So I'll do this on Friday, and we'll see the goldstone bond. Okay. So this, you should have seen that before. You can review this. Yes, you have a question?
Yes, you said that Sx squared and Sy squared are equal to identity on there. Because they are Pauli matrices, so if you square them, you have the identity. So it's just the what you wrote is just the identity.
But what happens here is that, I mean, I write this, but that's a very shorthand. I mean, this is Sx of Q, Sx of minus Q. Okay.
All right. Okay.
And remember, when there's a Q, there's a plus Q here. Yeah, that's a good question. If Q is different from 0, here you have this. So I will compute for the general case here, where I flip spins like this. Okay, I go from minus, let's see if I have K plus Q here, and I have K here. I will flip the spin from down to up. And so that's called the transverse susceptibility. Okay, because now I've chosen SZ. This is where my spins are. And Sx and Y is how they rotate. I hope I didn't make a mistake with factors of 2 here, but I mean, okay. Okay. I mean, it's a little bit, I'm sorry, I put it a little bit shorthand here, but yeah. You have to think of these as operators that have that are multiplied by C daggers here, and that are multiplied by C here, up, down, up, down. So when I multiply S plus times S minus, there are cross terms with Sy, Sx that don't commute. But when I add these two, the cross terms disappear. And what I will be computing is this. Okay, it's already too late. Okay, so see you Friday at 10. Bye-bye. I'll stick around if you have questions.
Thank you.